we talked about mirror-ray diagrams and how to draw a mirror-ray diagram. But some of you, when we talked about mirror-ray diagrams yesterday, you said, no, Miss Wilson, I love drawing all the lines, but can you please give me some math for the love of all things good and bright and beautiful? Well, good news for you. Today, we are going to do mirror-ray diagrams, but with math. Turns out you can do all the things that you can do with the diagram with math, and that's what we're going to do today. So, for mirror equations, we're going to find that there are two important equations that we can use for mirrors, and I'm going to give them both to you right now, and then we'll try a practice problem. Here's the first equation. The first equation is that 1 over the focal length for any mirror is equal to 1 over, and my computer's going to be super laggy. It did just wake up from a long nap. 1 over DO. That is the distance to the object. Write that down in your notes if that's something that you want to remember and you don't think that DO is going to be enough to help you remember that. 1 over the focal length equals 1 over DO plus 1 over DI, where DO is the distance to the object and DI is the distance to the image. This equation is, of course, worthy of your bag of tricks, and it is what we call the mirror equation. You could see that we could use this equation if we know focal length, we know the distance of the object, then we could also find the distance of the image. And I'll show you kind of what that means here. If you had a mirror like this, I'm going to draw a nice diverging mirror here. Let's say that I have an object right here. Let's say that I have an image right here. Okay. If you have a nice diverging mirror like this one, the focal length, as you know, is going to be that distance from the mirror here to wherever the focus or the focal point of the mirror is. That's our focal length right there. Then, and I'm just making this up here, obviously this isn't like the real focal point, I'm just making stuff up. But so it's our distance from the mirror to the focal point. The distance to the object is, we always measure this distance away from the vertex of the mirror. So it's the distance from the vertex of the mirror to the object. Finally, our distance to the image, DI, that's our distance from the vertex of the mirror to the image here. And I'll call this, oh wow, that was an enormous eraser. Let's try shrinking that down just a wee bit here. Wow, yep, really big eraser. Let's try like this. Okay, there we go, much better. We say that the distance here from the vertex of the mirror over to the image, we call that DI. It's your distance to the image. So those are kind of all of our conventions here for our, or I should say those are all of our variables that we use to describe all of these different distances here. Where DO is distance to the object, F is the focal length, and then DI is the distance from the vertex of the mirror to the place where all those light rays converge or would appear to converge to form an image. That's our first equation. Here's our second one. Our second equation looks like this. It's the magnification equation. We say M, which stands for magnification. The magnification is equal to the ratio of the height of the image over the height of the object. We can define those here on our picture. If this here, doop, doop, this is the height of my image. No, whoa, this is the height of my object. It's how tall my object is. This right here is the height of my image. It's how tall my image is. If my image is bigger than my object, I'm going to get a big number here. That's going to mean it's a number that's greater than 1. That's going to mean it's getting bigger. If the height of my image is less than the height of my object, I'm going to get a decimal here. That's going to mean that that object is, or that the image is smaller, that it's reduced in size. If they're the same size, then I'm going to get 1, and that means that there's no magnification at all. It's being multiplied by 1, which is itself, so it comes out the same height. Turns out that this is also going to be related to the distance to the object and the distance to the image. And here's how it's going to be related, is that the magnification is also going to equal negative di over do. Negative the distance to the image over the distance to the object. So whatever this ratio is of the image height to the object height, that's also going to equal the ratio of the distance to the image over the distance to the object with a negative sign here. And we'll talk about why that negative sign is there in a second. And this equation, which we call the magnification equation, is also worthy of your bag of tricks. Magnification equation. It takes so long to write because my computer is so laggy. Okay, perfect. There we go. We are set. Now, before we do a practice problem here, we got to talk a little bit about some sign conventions. Now, I could write all of these up for you, but it takes a long time to write, so I already went ahead and did it for you. Let's go here. Here are sign conventions that you are going to need to know. Yes, do write these down in your notes. If you need to pause the video to write them down, do pause the video and write them down. These sign conventions are going to be crazy important here and you're going to see once we start actually using these mirror equations, they are going to be such huge game changers that you're seriously going to need to know them. We say that focal lengths are positive for concave or converging mirrors. Focal lengths are positive for converging mirrors. Focal lengths are negative for diverging mirrors. Distances are positive for real images. Distances are negative for virtual images. Heights are positive for upright images. Heights are negative for inverted images. Magnifications are positive for upright images, and magnifications are negative for inverted images. Let me show you here a little bit about where these things come from. I'm going to start with these first four here, talking about our lengths and our distances. If you had let's start with a converging mirror like this. If you have a converging mirror like this, you're going to have your center somewhere like right here, and then you'll have your focal length or your focal point somewhere like right here. And so this right here, from here to here, this will be your focal length there. If, on the other hand, you have a diverging mirror will have its center over here and then its focal length somewhere, or its focal point over here, which means its focal length is right here. Notice here that the focal length is on the front side of the mirror for a converging mirror. You can see here's the focal length on the front side. This right here is the back side with the little lines that I drew. So the focal length is on the front side. Anything that shows up in front of the mirror we call positive. Here you can see that the focal length is actually back behind the surface of the mirror. It's behind the vertex. So we say that this focal length here is negative because it's back behind the mirror. Same thing happens for all of our distances. If you have a real image here, let's say that my object is right here, and let's say that, and this is like really poor. Okay, so just ignore, maybe I should just clear this out. Okay. Let's draw here. I'm going to draw another converging mirror. Nice converging mirror. Let's say that here is C, here's F, here's my object. Okay. My object is always in front of the mirror, so my distance to the object is always going to be positive. But check it out. Sometimes I'll get an image like this that's negative, or that's a real image out here. It's reduced in size, or sometimes it's enlarged in size. But actually, I'm trying to think if that's true. I might have just lied to you. This is a one-take kind of video, so if I ever say anything wrong, just like ignore it and keep going. Okay, but so here's the thing, is that you can see that the distance to the image here, this is my DO, like this. Here's my DO. Here's my DI. Do you see that the distance to the image is here in front of the mirror? This is in contrast with when you have a virtual image. Like if you had a nice diverging mirror like this, you had a nice virtual image here, This distance right here, this would be my distance to the object. This distance right here, this would be my distance to the image. Notice for a real image that's made up of real light rays, my distance to the image is positive because it's in front of the mirror, but for a virtual image that's made up of virtual light rays, my distance to the image is negative because it's back behind the mirror. We say that heights are positive for upright images and negative for inverted images. So here, this one, we would call this a negative height of the image because it's upside down. This here would be the height of my object. Height of object is always positive because it's always right side up. So here's my height of my object. Here, for this little virtual image here, I would have a positive height of my image because it's right side up. Lastly, magnifications are positive, once again, for upright images and negative for inverted images. A lot of students want to say that magnifications are positive if it's getting bigger and negative if it's getting smaller. That's not true. A magnification is greater than 1 if it's getting bigger, and it's less than 1 if it's getting smaller. But the signs actually show if it's right side up or upside down. Those are our sign conventions. You will need to know the sign conventions in order to do any kind of problem, like this one. Here we have a problem. This is from the Mirror Equations worksheet. Here we have a problem. We'll take a look at number 1 together. That says, a woman looks at herself in a magnifying makeup mirror whose focal length is 20 centimeters. If her face is 10 centimeters from the mirror, then determine the following. What distance from the mirror is her image? What is the magnification of her face? And then we're supposed to confirm the answers to parts A and B with a scale ray diagram. Let's take a look here. Here's the situation. You have a mirror that looks like this one. This is a converging mirror. You can see if you look to the side, it's a nice little concave mirror here. The reason why I know it's a concave mirror is because there's only one type of mirror that can actually magnify images or create an enlarged image. Diverging mirrors can't do that. As we talked about yesterday, all diverging mirrors are going to make images that are upright, reduced, and virtual every single time, all the time. Concave mirrors like this one, converging mirrors, actually can make enlarged images. Here's what you see right now, is right now you can see my classroom here, and my classroom is inverted, it's reduced in size. But if I take my finger here, and I start with my finger far, let me aim well, okay, yes. I start with my finger far away. If I bring my finger closer and closer and closer and closer, then you'll see that I can get an image of my finger here, sorry, trying to show this to you. I can get an image of my finger that is actually enlarged in size, that is upright like this, in contrast with if it's far away. If it's far away, you get a reduced in size that is inverted, but nice and close, you get enlarged in size like this that is upright. This is how all makeup mirrors work. If you're far away from the mirror, like really crazy far away like this, if you're far away from the mirror, then the image that you're going to get is going to be inverted and small, but as you get closer, you get to a place where you get an actual image that is nice and big and magnified. And that's how every single makeup mirror works. Hey, you'll notice also that there's this weird point, and I don't know how well I can show this to you. Let me see if I can get it. Okay, there's this weird point right here where I actually don't get an image of my finger at all. Do you see how it's just like a blurry mess of color? That's when my finger is right at the focal length. If my finger is further back than the focal length, I get a smaller inverted image. If my finger is closer than the focal length, I get a upright and enlarged image, but if my finger is right at the focal length, like here-ish, I don't get an image at all. So here's what you see in this problem. You see a woman who has her face close to the mirror. It says that the focal length is 20 centimeters and her face is 10 centimeters from the mirror. So it's going to be magnifying her face. The question is, what distance from the mirror is her image, and what is the magnification of her face? And then can you confirm the answers to parts A and B with a scale ray diagram? Let's see what we can do here. I'm going to try to shrink this up here. We're going to see how this goes. We're doing great, we're doing awesome. Yeah, we're doing so awesome, except that I can't get it to the place that I like it. But it's okay, it's really gonna be fine. I just wanna be able to see it. Okay, you know, well. Okay, in my brain, this was all gonna go just super marvelously. Okay, come on. You can do it. Okay. Okay, here's what we're gonna do. I'm gonna bring this over here so that we can still see it. Then I'm gonna pull this up here. I'm gonna shrink it up a little bit so then we can look at the problem while we do our work over here. Ideally, that was the idea. That was the vision. I don't know if it's gonna happen, but you know what? We're doing our best. Okay, yeah. We're gonna go with that and see if it works. And if we hate it, well, we'll never do it again. Okay, let's try this problem. This is question number 1. Oh yeah, this is for sure not gonna work unless I shrink this down. Oh, that's as small as it goes. Okay, scratch that. You know what? That was all really fun. I loved playing around with how to get this set up, but we're not doing that because it's impossible. Okay, instead I'm just gonna write over here and then I'll tell you what the numbers say. Wow, that was just an epic fail. But that's okay, it's fine. You guys are so flexible and awesome and you just like deal with stuff and I just love that. Yes, thank you for your flexibility. Okay, we're gonna start here. I'm going to erase this. We are going to keep these 2 equations up here because we're going to be using them both. Let's start here. This is question number 1. Okay, here's what we've got. We have a few pieces of information. We know that the focal length of the mirror is 20 centimeters. We know that the distance to the object, that is the distance to her face from the mirror. It says that the distance here is 10 centimeters. That's how far away her face is from the mirror. And then we're going to start with part A. In part A, we're looking for the distance to her image distance, how far away her image is from the mirror. Now, here's what we're going to do. We're going to start with our mirror equation. 1 over f equals 1 over dO plus 1 over di. Now, in a second here, I'm going to start rearranging to solve for di, but before I do, let's check our positives and negatives here. First, my focal length. This is a converging mirror, and a converging mirror has a positive focal length, so I'm going to put a little positive in there. My distance to my object is always going to be in front of the mirror, so that is always going to be positive. If you know your mirror ray diagrams well, you'll know if what we're about to see is going to end up being a virtual or a real image. And so you should know a little bit in your head about what this sign should look like, but we'll confirm it with a little diagram later. Now that I've written my knowns and unknowns, I've written my original equation, and I've checked all my signs, now I'm ready to play. First, I'm looking for di. So let's get di on one side of an equation all by itself. What I'm going to do is I'm going to subtract 1 over do from both sides, and I'm going to get something that looks like this. 1 over di equals 1 over f minus 1 over do, like so. Now, here's the thing. We got a situation here, a very serious situation, because this is in the denominator. And these are also in the denominator, and I need this to be in the numerator. Now, I'm going to show you a little trick that's going to work for our algebraic rearranging. You can use this trick if you like. If you like doing this other ways, then you can do this algebra other ways. Your algebra is up to you. But I'll show you the way that I like to do it. Here's what I like to do first. Do you agree that I could just rewrite this whole equation like this? Doop. 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 Just like this. And that's the same exact equation. I've just written, instead of writing a 1 over, I just did it to the -1. But it's the exact same thing. Now check this. If I want to get this in the numerator, I can take this whole side to the -1, and I can take this whole side to the -1. That effectively cancels out these two -1s, and I get an equation that looks like this. di equals f -1 minus do to the -1, and then all of that together to the -1. What I like to do is I like to just plug in numbers here like this into my calculator, and I just plug in these little -1s, and it takes care of flipping everything for me. That's how I like to do it. If you prefer instead to write this as a fraction like this, DI equals 1 over F minus 1 over DO. If you like to write it like that, you can totally write it like that, and that's a totally fine way to write it. I've just found that students, when they're trying to type this into their calculators, they can kind of like lose track of where all the 1 over 1 things are, and so then they just blah, 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 and everything gets messed up. They forget to put parentheses in here. They have all kinds of issues. When you do it this way, it keeps it as a nice, clean, simple algebraic expression. So now what I'm going to do is I'm going to plug in numbers here. I get that DI, the distance to the image, is going to equal. Now here's what I'm going to do. Normally I would convert these into meters, but I'm just going to leave everything in centimeters because then my final answer is going to be in centimeters, and that's going to totally work out great for me. So I'm going to write this as 20.0 centimeters to the -1 minus 10.0 centimeters to the -1, all of that to the -1. Type it into your calculator. Go ahead and try. And what you should get is that the distance to the image is equal to -20 centimeters. And there you go. Hey, check it. We got a negative sign here. Tell yourself, what does that mean about the distance to the image? What does that mean about the image? Is it a virtual image or is it a real image? Does it tell you anything about whether that image is upright or inverted? Here's what you should say. You should say, this negative sign here tells me that that image is going to be a virtual image. It's made up of virtual light rays. And then you should say, no, it doesn't really tell me anything about whether it's upright or inverted. I just know that it's a virtual image. Okay, that's part A. Let's try part B. I'm actually going to do something unconventional here. I'm going to start part B up at the top of the paper. What? Yeah, I know, I just don't feel like getting out anything. Okay, here we go, part B. Part B asks, what is the magnification of her face? That's the question. Now, there are a few different equations that I could use. I could use the height of the image over the height of the object, but you can see I wasn't actually given here the height of the image or the height of the object, so that is going to be a really tricky one to use. But here's what I could do. Didn't I just find DI? And I was given DO? So here's what I could do. I know that DO is equal to positive 10.0 centimeters. I also know that DI is equal to negative 20.0 centimeters. Now, you know that in my class, I say that if you can avoid it, you should never use the answer to a previous question to do the next question. However, in this case, there is really no way to avoid it. There's no way to do it differently. So we can use our negative 20 centimeters here. I write that my magnification is equal to negative DI over DO. That's going to be negative 20.0 centimeters, but that 20.0 centimeters is also negative, so I got two negative signs in there. My DO is positive 10.0 centimeters. You could do that one in your head. You get 20 divided by 10, that's going to give you 2, check our sig figs here, 0.00 is your magnification. Notice here, my units of magnification, I got none, because it's just how many times you multiply the height of the object by to get the height of the image. Notice that her face is going to be 2 times bigger than it is in real life. And we get an answer that is positive 2. Positive. Think about it for a second. Check your sign conventions. What does that tell you about the image? Did you say that the image is going to be upright? Because that's what you should say here. If you get a positive magnification, that means your image is going to be upright. And that is a little practice with some mirror equations. But that's not the end of the problem. If you check the problem, it says, oh wait, that's my sign conventions. No, although I do love my sign conventions. Hello, sign conventions, so good to see you. You're not my end destination though. Okay, here we go. If you check the question, it says, confirm your answers to parts A and B with a scale ray diagram. Here's what that means. You are going to then, for part C, draw a mirror ray diagram of this situation. And when you draw it, you're going to draw it to scale. Now, this is something that I'm going to be hand wavy with in my video because of my physical limitations and the fact that I cannot use a ruler in order to do this kind of problem, but you would have to use a ruler in order to do this kind of problem. Here's what you would do for part C. For part C here, oh gosh, oh no, okay, wow, that was dangerous. Okay, for part C here, here's what you're going to do. You're going to draw a to-scale ray diagram. What that means is you're going to draw a ray diagram like the ones that we've been drawing, but you're going to draw it with all of the lengths proportional to the actual lengths in the problem. Here's what we got from the lengths of our problem. We got that the focal length of this mirror was 20.0 centimeters. We know that that's positive because it's a converging mirror. We also got that the distance to the object is equal to positive 10.0 centimeters because it's in front of the mirror. And now we're going to draw a little diagram here. When you draw this diagram, you're going to start by drawing your principal axis. Then you're going to use your compass to draw an actual mirror that has an actual focal length of 20 centimeters. Now, you're probably not going to actually draw a mirror that has a focal length of 20 centimeters because 20 centimeters is probably not going to fit on your page. So you're going to choose a scale that seems appropriate. For your piece of paper, it's probably appropriate that 1 centimeter on your paper is equal to 10 centimeters in real life. If you have a mirror that has a focal length of 20 centimeters, check it. What does that mean that the radius or the distance to the center of curvature of your mirror is going to be? Did you say that, well, Miss Wilson, you see the distance to the center is always 2 times the focal length, because the focal length is just half the distance to the center of curvature. So what you should be saying right now is, well, that means that my distance to C is going to be 2 times 20 centimeters. You should say, yeah, Miss Wilson, that means it's going to be 40 centimeters. Here's what you would do now. Oh, no. Ah! Okay, I left my compasses in my back room. This is a problem. I got my giant compass. Here's what you're going to do now. You're going to take your compass, you're going to adjust it so that the radius here is exactly 4 centimeters, or 4, depending on your compass and the size of your scale. So you're going to measure so that the distance between the point of your compass and the marker of your compass, or the pencil here, should be 4 centimeters. Then you'll place the center of your compass here on your piece of paper, and you'll trace out a circle that has a radius of 4 centimeters. So it's nice and to scale. Once again, I can't do this here because I can't use a compass on my computer, but what you should get is you should get something like this here. This distance from here to here is going to be 4 centimeters, which is what you set. So here's your C. Here's your focal length. Your focal length should be 2 centimeters away from the vertex of the mirror. Once you do that, now you're going to draw the distance to the object. It says that the distance of the object is 10 centimeters. For your scale, that means 1 centimeter. What you're going to do is you're going to start at the vertex of your mirror. You're literally going to take out your ruler here, and you're going to measure from the vertex of the mirror 1 centimeter away. It should also be 1 centimeter away from the focal point because the focal length is 20 centimeters. This is where you will draw your object. Then, once you draw your object, you will follow your 3 golden rules to make an image. And what you should get is an image that shows up at, because you got DI, you said that DI is equal to 20 centimeters, and it's negative. When you draw this, you're going to draw one light ray that's parallel that then bounces off at an angle that would go through, oh gosh, wait, let me see how I did this. Oh yeah. Your light ray that's parallel bounces off at an angle that would go through F. Wait, that doesn't make any sense to me. Why am I so lost right now? Gosh, well, this is what happens when I try to do things in one take. Okay, so I'm going to start with my first rule. A light ray that goes through C will pass back through C. You'll do a light ray that would go through F here, will go back parallel like this. Then you'll do a light ray that goes parallel, would go back through F like this. You'll trace back each of your lines like this. Of course, you will do this with a ruler. It'll all be to scale and beautiful, and you'll get something like this. Now, mine is terrible and awful because I didn't do it with a ruler. This is where you actually need to be very precise. But then what you're going to do after that is you're going to measure here your distance to your image. You'll measure your DI. And when you measure your DI, you should get that this measurement here is 20 centimeters. Measure it with your ruler, and you'll measure about 2 centimeters, which with your scale translates to 20 centimeters. Then you will go ahead and put in a negative sign here to show that DI is negative because it's a virtual image. Then the next thing that you'll do, because we're trying to confirm all our answers, is you're going to measure here the height of your object. And when you measure the height of your object, I'm going to change my color here. When you measure the height of your object, you're going to measure it. Normally, I like to set it, so sometimes I'll just do this here for myself, and maybe I'll say when I originally draw my object that it's 1/2 centimeter, which equals 5 centimeters. So you'll make this measurement. Then you'll measure the height of your image here. What you'll then do is you'll say, what's the magnification like? And you'll take the measurement of your height of your image, divided by the measurement of the height of your object. Plug in the numbers that you actually measure here, and that should give you a magnification of 2. So you should be able to confirm using a diagram exactly what you did with the math. And that's part C. Of course, you're not doing it the sloppy way that I did it because mine won't be to scale. You would do it the actual formal way with a ruler and straight edges and a compass and all of those good kinds of things. And that, ladies and gentlemen, is mirror equations. I hope you have fun with the rest of your mirror equations work, and I'll see you all later. Have a great, great rest of your day. Bye, good people.